Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And I see there are all kinds of questions that have come in. Let's see. There's one here from Aaron. Are all pixels squares or rectangles, or have other shapes been used? Well, another candidate shape will be hexagons. And if you take, for example, let's say you take a bunch of coins, all identical, and you kind of push them together, they will arrange themselves. The closest packing of those coins will be a hexagonal packing. So you'll make a bunch of little hexagon shapes there. It's kind of like the same shapes, same sort of structure of shapes that you would find in a beehive. This is just the way that packs circles closest together. And there are lots of places where you'll see things that are packed together like that form a hexagonal array. You see that in tilings in different places and so on. Well, for example, the retina of our eye, the cells are arranged in a roughly hexagonal pattern. So in a sense, the pixels that we have in our eyes are roughly hexagonal pixels. Now, people have tried using hexagonal pixels both for cameras and for displays, more so I think for cameras. Back in the 1950s, when people were first trying to do optical character recognition, I think some people tried using hexagonal pixel arrays. By the way, insects, for example, which have these compound eyes with ommatidia, where they've got lots of separate little pieces of their eye that separately sense light, those are typically arranged in a hexagonal grid. So each pixel of an insect eye is effectively hexagonal. Now, just to say something about how optical character recognition works. So the problem one's trying to solve there is you've got a picture of a letter A, for example, and you want to recognize that it is the letter A as opposed to a B or C or whatever else. And at this point, the state of the art in doing optical character recognition is quite good. So long as the image is high enough resolution, it really has a hard time if there aren't enough pixels per letter. But as soon as you have, 50, 100 pixels across each letter or something, it's really no problem at this point to be able to recognize that's an A, that's a B, et cetera, et cetera, et cetera. A cool thing we did recently, actually, for Wolfram Alpha, for those who use that, the Wolfram Alpha app now does math OCR. So in a kind of convenient, if you want to enter some math formula and you have it printed in a book, it could be a question in some book or something, you can just use your phone to take a picture of that question and we'll figure out what that math formula was based on just the image of the math formula. We're talking about OCR in general. How does it work? So the first OCR that people did in the 50s and 1960s was just digits, so 0 through 9. And so, for example, people wanted to do that when there were checks that people wrote. If anybody even writes those anymore, I don't know. Yeah, they must do. I know they do in certain kinds of settings. At least you'll have a check and you'll write out, $372 and no cents or whatever, and then you write the digits 372. Well, one of the first applications was automatically reading checks and reading those digits 372 or whatever from the thing that was written by hand. But an easier problem is actually a different application, which was an early one, was reading books for visually impaired folk, where you could take the book, which is after all printed, and you could get it recognized by a computer so the computer could speak off the words that were in the book. But so optical character recognition is vastly easier when you're dealing with printed text because every A looks more or less the same. It may have aligned itself differently with respect to pixels, and the ink may have landed a little bit differently on the paper, but basically every A is the same. When it comes to handwriting, that's not the case. When there are digits, you have a small enough number of digits to choose from that you can start to recognize things. But if you're dealing with ordinary handwriting, and particularly when it's cursive and things like that, it's rather difficult. And even today, one doesn't really have systematic ability to do character recognition on handwritten stuff, but you can on printed stuff. On printed stuff, it's really good. So how does it work for printed things? So what people did, even from pretty early on, was you take the array of pixels that corresponds to the A. First of all, you have to kind of line up, where is the letter? Okay, you've got the sort of bounding box of this is where the letter is. You divide that region into pixels, and then you say, which of those pixels have black ink, which of them do not? And then you have to recognize, given this pattern of where the black ink is that an A, is that a B, is that a C, et cetera, et cetera, et cetera. Actually, this was a very early application for neural networks. Became, even in the 1960s, I think, people were doing this, of using sort of, what you were doing was basically saying, you've got an array of, let's say, I don't know, 100 pixels, a 10 by 10 grid of pixels. And you say, if this pixel is on and that pixel is off and this pixel is on and so on, you've got all these different combinations. And you say, with this pattern, which letter is it most likely to be like? And so there was this kind of scheme where you are using one of these artificial neural nets where you're basically saying, take one particular pixel, pixel number 17 or something, and then compare that with pixel 18 and pixel 24, and then take the first pixel with a weight 0.1, another pixel with weight minus 0.2, another pixel with weight 0.3, take the blackness or whiteness as a 1 or 0, multiply that by the weight, add all those numbers up, then say, is the result, let's say, greater than or less than 0? And then make from those, for each of those kind of, you're thinking of it like a neuron in the brain. One has a given neuron will have dendrites that kind of collect information from lots of other neurons. They're kind of like little wires that are part of the nerve cell. And when those dendrites will be sensing whether other nerve cells to which they are connected have fired or not. So this is kind of an imitation of that, where you're saying you connect these kind of these things with weights and so on to these different pixels, and you say what combination of pixels is on with what weights and so on. And then you simply learn, typically when there's an A, these pixels with these weights will be turned on and these ones will not be. And that's how, from the very earliest days of optical character recognition, that's pretty much how it worked. In modern times, with modern deep learning neural nets, we have many more of these combinations of pixels and weights, and you have multiple layers where you'll do one round of sort of combining things with weights and so on, and then another round of that, and you'll do various kinds of thresholding and so on. It's possible to set it up so that if you could only learn what the right weights and connections and so on were, you could be very accurate in saying that's an A, that's a B, and so on. And the thing that is now sort of routinely done is training these neural nets in a systematic way, where you say, let me show you 1,000 examples of A's, 1,000 examples of B's, or 100,000 examples of A's, 100,000 examples of B's, and you can, and based on those, you can say the A's tend to work this way, the B's tend to work that way. You arrange these weights and so on so that you can discriminate between these different kinds of letters. Now, the more different kinds of letters you're trying to discriminate between, the more difficult it gets. So, for example, it was routine to deal with digits, even handwritten ones, by I would say the 1970s. In terms of letters of the alphabet, the English alphabet, for example, in books, that was pretty routine by the 80s. In terms of sort of a bigger sort of discrimination problem is things like, don't just discriminate between letters of the English alphabet, do all the Chinese characters, whatever it is, some number of tens of thousands of them, or alternatively, do, like images of cats and dogs and things. And those are things that only really became practical in the last 10 or so years. And that's sort of the modern machine learning revolution is associated with that. Optical character recognition was already doable before that. All right, very long explanation about different kinds of shapes of pixels and so on, but people did use hexagonal pixels for some of the early optical character recognition kinds of things. there's also some technologies for flexible screens, for example, where you can deform them. You're not distorting the shapes of the pixels, but you are certainly taking what was kind of a nice ordinary square and you are deforming it in the third dimension. And not sure how useful those things have yet turned out to be, but that's a technology that's starting to be possible. Let's see. Okay. Antti is asking, why hasn't all the cosmic background radiation escaped out into the universe by now? How is it still around to be detected billions of years later? Okay, this is kind of a tricky geometry kind of thing. Okay, so the cosmic microwave background comes from close to the beginning of the universe. The universe started in this kind of big bang, where the universe started as this ball of hot stuff, probably infinitely hot stuff. According to our recent theory of physics, probably infinite dimensional, infinitely hot stuff. And gradually the temperature went down, the dimension went down. And what was happening was, at the beginning, the universe was a bit like a star, like the sun. You can't see into the sun. The photons that you see from the sun are all coming from the surface of the sun. Inside the sun, photons are kind of bouncing around, and they're gradually sort of moving around inside the sun. They keep on getting scattered by another atom in the sun, or another nucleus in the sun. It takes like, I think, 10 million years or something for a photon to get, on average, from the center of the sun to the outside. So the sun is not transparent. You don't get to see into the sun. And you also don't get to see into the primeval fireball, the initial thing in the Big Bang. All you can see is kind of the surface of that. Well, what happened is, as things cooled, there came this moment when this hot gas became transparent. When it was hotter than, how hot? Some number of thousands of degrees, I forget exactly how many. It was not transparent. It's kind of like fire, or like the sun. It's something where photons of light keep on getting scattered. They can't just get through it as a transparent thing. But then sometime around 100,000 years after the beginning of the universe had cooled enough that it was no longer, the content of the universe was no longer like fire or like a star. It was like ordinary gas that was transparent. And so all the photons that we see, the light, the radiation that we see, comes from that moment when the universe became transparent, and we're kind of seeing to the things, the photons that were emitted just before the universe became transparent. It's often called the last scattering surface, where the photons were last scattered before they just started moving freely through the universe. Now, of course, they don't move completely freely through the universe, because, for example, a photon that started its journey right when the universe became transparent 100,000 years after the beginning of the universe, 14.5 billion years later, it may be that you have a detector that detects that photon. So that photon has existed all that time, all that 14 billion years. It's been just traveling through the universe, and then splat, it hits your detector, and you measure, oh, I saw that photon. So that's what's happening when you're detecting something from the cosmic microwave background. Now, one question you might ask is, if that last scattering surface, if the temperature of things was some number of thousands of degrees, maybe 6,000 degrees or something, how come these, and it was something that corresponded, that's a temperature that corresponds to something like visible light, how come the photons that we detect in the cosmic microwave background are microwave photons that have much lower energy? And the answer is, that's because of the expansion of the universe. And it's because and this is where the geometry gets kind of tricky. Let's see, how best to explain this. Let's take a slightly different tack here. Let's say you're looking out into the night sky, and you see a star in the sky, and the star is 10 light years away. That means that the light that hits your eye that allows you to see that star, that light, in some sense, started its journey 10 years ago. And it moved at the speed of light from that star to your eye, and now you see it in your eye. But so that light is, in a sense, 10-year-old light coming from that star. Okay, so now let's look at a star further away. Well, maybe you can look at a star that's 1 billion light years away. That means that the light that comes to your eye now started its journey from that star 1 billion years ago. Okay, let's keep looking further and further, at stars that are further and further away. Eventually, you won't find any stars anymore because you're asking for things that were like 14 billion years old. 14 billion years ago, that was a young universe before any galaxies had formed, before there were any stars. And what you're seeing is, right, yeah, a little bit, I think around that time, first galaxies were forming. But you can look long enough ago that there weren't any galaxies, there weren't any stars. What do you see if you look out into the night sky and you're seeing a thing that was that old? Well, the answer is you're seeing back into that last scattering surface. You're seeing the Big Bang, so to speak. You're seeing the place where the Big Bang, the time when the Big Bang became transparent. But what do you see in each different direction? Well, the point is, in every direction, you will see the Big Bang. And it's a little bit hard to understand because you'd say, well, isn't the Big Bang this thing that's sort of a lump in one place? Well, the point is that the lump in one place, we're sort of inside that lump. And so whenever we look sort of in any direction, we will see to that place where that initial sort of primeval fireball first became transparent. Now, it's not an obvious fact that there are sort of holes in the night sky where you get to see all the way back to the Big Bang. It could be the case that every place you look in the night sky, there's a star or a galaxy right there. Could be the case that there's, let's say that the galaxies were uniformly distributed throughout the universe. Then it would be the case that pretty much every direction you look in, there would be a very high chance that you would see a galaxy. Turns out that galaxies are clumped as a result of gravity. And that's kind of why there are holes you can kind of look through, so that you're basically seeing past all the galaxies back to light that started its journey at the very beginning of the universe, or 100,000 years after the beginning of the universe. So essentially what's happening is that when the photons that were produced at the beginning of the universe just got sent out in all directions, and some of those directions are ones that lead to where we are in the universe today. And all those photons, the reason that they're still out there in the universe is because they didn't encounter anything. They went just as photons going on a journey that lasted 14 billion years, and finally we detected them. Now, an interesting fact is, because of relativistic time dilation, to that photon, no time will seem to have passed. One of the features of relativity is that when an object is going very fast, the effective speed at which time passes is progressively slower. And if you're going at the speed of light, the speed at which time passes it doesn't pass at all. So to that photon, it's as if no time passed. It's like, as far as if the photon, which it can't, was kind of, if it had some whole sort of mind and was thinking about what was going on, to the photon, it would be like, I was just emitted. Nothing happened. Oh, I'm just absorbed 14 billion years later, but no time will have been perceived to pass. In our theory of physics, we can kind of understand in a rather mechanical way why this time dilation process happens. See, the thing is that a particle like a photon or an electron, all these things are created from kind of sort of structures in this giant kind of network that represents the structure of space. And these particles, it's like kind of like a vortex in a fluid, for example. The vortex in the fluid, it's kind of like an eddy that's going around, but there are molecules bouncing around. If you looked at a microscopic scale, what you're seeing in that eddy is some collective effect of lots of those individual molecules bouncing around. Well, similarly, we think particles like electrons and photons are that same kind of thing, but instead of little molecules bouncing around, there's this network that represents the underlying structure of space. Well, when a particle is in one place, the particle, that network that represents the structure of space, is continually being changed. And a particle can either exist at a particular place in space and progressively be changed by the updating of this network, or the particle might be moving, and then the particle has to essentially recreate itself in different places in space at every moment in time. And the thing is that it sort of uses a certain amount of computational effort to recreate itself at the same place, but it is using, if it's moving, it's using some of the computational effort that it has, some of the computational capability it has, it's using to recreate itself at a different place in space. And so it doesn't have as much sort of computational capability to sort of update itself in time, so to speak. So if it's in one place, it can use sort of all of its computational capability to just say, I'm changing in time in this way. If it's also moving in space, some of that computational capability has to be to recreate the particle in a different place in space. So essentially, that's why time slows down if you're going faster, because when you go faster, what that means is that you're recreating yourself at a different place in space, and you're using some of the sort of computational ability that exists as a result of the underlying structure of the universe. You're using some of that on motion, and you don't get to use as much of that on the progress of time. For a photon, it's an extreme case where you're kind of using all of that computational ability for motion. You don't get to use any of it for progression in time. And that's why it seems like no time has passed for something going at the speed of light. Let's see. All right, let's take a look at some other questions that come in here. WWW is pointing out it's weird to talk about time experienced by a photon. I say it experiences only 2 moments of when it is produced and when it's absorbed. Interesting claim. So, well, it depends on the, okay, if the thing that was there was, let's say, an atom, has a nucleus, a bunch of electrons. If it was even a proton that has a bunch of quarks and gluons and so on in it, when a proton is produced, you're producing this thing that is a, it's 10 to the minus 15 meters, 1,000 trillionth of a meter across, but it's got a whole structure inside it. We know that it has a structure inside it, and it consists of quarks and gluons. There are 3 basic quarks in a proton, and then there are lots of quark-antiquark pairs, lots of gluons that's continually sort of exchanging these gluon particles that's kind of holding the proton together. But that proton has a whole complicated structure inside it. We know that. And so it is the case that a proton that, when you take a proton and you make the proton, you accelerate it in a particle accelerator to 99.999% of the speed of light. That proton will experience less time passing. And I think experience is not used so foolishly in the case of a proton, because the proton has all this stuff going on inside. So all those quarks, and they're interacting with gluons, and they're doing this and they're doing that. All those interaction processes are happening sort of more slowly, at least as viewed by an observer who isn't moving, when there's a proton going very fast. So I think it is fair to say that sort of a proton, when I say experience, one could interpret experience to mean sort of the experience of a human-like observer kind of getting things into a mind and so on. I don't think we're attributing quite the same type of thing to that individual proton, although I'm not sure ultimately how different it is. But there are certainly things that are happening inside the proton as a result of sort of the way the proton was produced, et cetera, et cetera, et cetera. In the case of electrons and photons, we don't yet know whether they have an inner structure. In traditional physics, when I say traditional physics, I mean physics from the 20th century primarily, the electrons are thought to be sort of perfect geometrical points of 0 size. Right now, we know that electrons are bigger than a they are certainly not bigger than a millionth the size of a proton. But if you said, could they be a trillionth the size of a proton? We don't know. We don't know. The way that we get to know how big we think electrons might be is by crashing electrons into each other and seeing how they scatter. And we know from those kinds of experiments, more or less it's those kinds of experiments, that electrons certainly can't be bigger than a millionth the size of a proton, maybe a 10 millionth the size of a proton. But smaller than that, we don't know. In our models of physics, electrons do have a non-zero size. It's pretty small. It's like, I think, 10 to the minus 81 meters, as I remember, is one estimate that I had of it. I remember that number particularly because when I was a kid, I was interested in particle physics. And at the time, it looked like there were some experiments in particle physics that might have suggested that electrons were not zero-sized objects. And I guessed that electrons might be 10 to the minus 18 meters, which would be a thousandth the size of a proton. At the time, one didn't know that from experiments. That turns out not to be correct. And so now sort of the guess is it might be 10 to the minus 81 meters rather than 10 to the minus 18 meters. Are vastly smaller, but it's just kind of funny that the digits are the same, just reversed. But in our model of physics, both electrons and photons have non-zero size. They come from many different pieces of the underlying structure in the universe. Now, I have to say, one of the things that I kind of suspect is that the way that you get something like an electron or a photon, it is made from this sort of tangle of connections in the underlying network that represents the structure of space. Well, other things that are made from sort of the structures that just exist in space are black holes. Black holes are places in the universe where gravity is strong enough that it prevents kind of light from escaping from some region, and you have this kind of deformation in the structure of space that represents the black hole. Black holes are pretty big, at least the ones that we know exist that come from collapsing stars and so on are big, on the order of kilometers and things like this in size. But I kind of have the suspicion that in the end, it will turn out that one can look at particles as being like very tiny things, very much like black holes. And one of the features of that is for a big black hole, like a black hole that might be something that we would observe in a black hole collision in the gravitational wave detector or something like this, those black holes come from the collapse of stars. Stars are a bit more massive than the sun, but when a black hole, when something as massive as the sun collapses as a result of a supernova explosion or something like this, it can kind of fall in on itself and be crushed by gravity and eventually form a black hole. But when it falls in on itself like that, you know, if there had been some civilization that had a whole structure that was around that star, it probably would have been pulled in by gravity and crushed into the insides of that black hole. So inside a black hole, there can be all kinds of structure. It may be kind of a mess in there, but there's all kinds of structure in there. Outside a black hole, no light escapes from the black hole. We don't get to see anything about the black hole other than just, oh, there's a black hole there, and it has certain gravitational properties. So what that suggests is that when we look at something like an electron, one of the big mysteries actually in physics is the fact that all electrons seem to be the same. They're different in the sense that they might be going in a different direction, with a different energy, but all the electrons, for example, have the same mass and have they all seem to be the same. And one feature of black holes is that even though the innards of the star that got crushed might be completely different from outside the black holes look the same, except for their size and how fast they're spinning around. And so it's sort of a little bit like with particles, where all the electrons look the same, at least from the outside, because we're not in the inside of the electron. And so it could be the same thing as happens with black holes, that sort of from the outside they're all the same, but there's an inside where there can be all kinds of details that are different. And so that sort of affects this, you know, what can be happening inside the electron. Well, we won't know because we're on the outside, just like we were on the outside of a black hole, but there can still be an inner structure that exists there in some sense. Okay. Let's see. Okay, William asks, do you need mass in order to store information? Can you have an organism made purely out of photons or other particles moving at the speed of light? Interesting question. I have a friend who's was a physicist, then was in the technology industry, who has this kind of, I think, slightly wacky theory that if you imagine this sort of end point of a civilization that has technology and all that kind of thing, that in the end, the way to kind of exist for the longest time in the evolution of the universe is in the form of something like light. And, you know, just as I mentioned, these photons can be going for a very long time through the universe. You can imagine you turn sort of the thoughts of a human into something where it's just a bunch of photons and so on. And those photons are traveling for 1 billion years through the universe. And maybe they finally hit a grain of dust and they're then scattered in some different direction and so on. So my friend has this sort of theory that, and I think he kind of relies on some things that I've done to kind of argue that you could imagine making a kind of universe-sized brain out of essentially the exchange of photons, where just like in our brains, you know, one neuron will signal another neuron electrically and takes 1,000th of a second for one neuron to signal the neighboring neuron. But you could imagine a situation in which you're sort of signaling across this giant brain that is the whole universe, and you're using light signals, and those light signals take 1 billion years to arrive at the next sort of place where they're going. But I don't think, one of the difficulties is, okay, let's see. One of the problems is that if you have things going at the speed of light, if you have two photons going in opposite directions and they hit each other, you could ask what happens. Well, in a first approximation with photons, they kind of just go through each other. But there's a very small probability of what's called light by light scattering, which is a process by which a photon can interact with another photon. Actually, it happens by forming very briefly a virtual electron-positron pair, and the other photon kind of interacts with the electrical charge that was formed in that electron-positron pair. But most of the time, it's kind of hard to, well, I think you end up with something where, let me think about this for a second. Yeah, I mean, it's hard to know how you build something just out of light. If you have mirrors and you have light bouncing around and so on, that's all well and good. You can use light like you can use electrons in a computer to transmit information, but you have to have other stuff like the mirrors and so on to reflect the light. If it's just light, you can ask the question, could you ever imagine, even if you were prepared to have things take 1 million years to happen, could you ever imagine making a thing that was just made of light? And I think, well, that's an interesting question. Okay, yeah, I can think of a way you could do it. If the light is traveling through ordinary flat space, it's not going to work because you just have a photon, it's just going and it's trundling along. Unless it hits something, the photon's just going to keep going in a straight line. And those parallel lines, you'd have two photons and they're both going in parallel lines. In flat space where there's no gravity, those photons will just never meet. Okay, however, if there's gravity, you can have a situation where the space-time is curved and the paths of light are no longer straight. And for example, in a simple case, one thing that's been extensively observed now is gravitational lensing, where if you have a mass like a galaxy or something, you have photons that are going near the galaxy, they will be bent by the presence of the galaxy. Just like if you send a spacecraft past a planet, the force of gravity from the planet will cause the spacecraft to be deflected and to sort of almost be pulled into the planet. Well, the same thing happens with photons. Actually, the photons have actually twice the effect that ordinary particles have, because they have gravitational magnetism as well as gravitational electrical-like forces. They have gravitational magnetic-like forces. That was a big prediction of Einstein's theory of general relativity in 1915, was that the bending of light around the sun will be by twice as much as it would have been in previous theories. And that was supposedly observed, not a very good experiment, but it was supposedly observed in 1919. It's now been observed in much more detail. But that's what happens with gravitational lensing, is that the light from a distant star is bent by the presence of mass in a galaxy, and it's kind of like the galaxy acts like a lens, sort of focusing light and so on. Okay, so the extreme version of that is in a black hole, particularly a spinning black hole. There can be photons that actually orbit the black hole. So they're pulled in by the force of gravity of the black hole so strongly that even though they're going at the speed of light, you can orbit in a black hole. You can orbit at the speed of light. So when you're orbiting the Earth, you orbit at 17,000 miles an hour. When you orbit the sun, you are orbiting, I don't know what it is, it's probably about 60,000 miles an hour, something like that. If you had an orbit, a low sun orbit close to the sun, you probably get pretty hot there. But every different object of a certain mass and size has a certain orbital velocity. For a spinning black hole, the orbital velocity is basically the speed of light. And so that means that you can actually keep a photon in orbit around a black hole. And so I think it would be the case. I could imagine a situation in which you could have photons that were orbiting a black hole could have, I mean, this is very exotic, but photons orbiting a black hole, normally they would just pass through each other without having an effect. But the thing I mentioned before of light by light scattering would happen for those photons, not at a very high rate, a very low rate actually. But it would occasionally these photons would interact with each other. And so the incredibly exotic kind of make a mind, make a computer out of something would be a whole grid of photons all in orbit around a black hole, and all interacting very slowly, very occasionally through light by light scattering. Now, one bug in this idea might be that my recollection of the way general relativity works is that when you have a rapidly spinning black hole, you can have this phenomenon of photons being in orbit around it. I don't think you can have that for a black hole that isn't spinning. And so I think you need the phenomenon called frame dragging. I think you need that in order to get this orbit of a photon around a black hole, which would mean that the photons could only orbit around a rapidly spinning black hole, and they'd only orbit in the direction that the black hole is spinning. It would be like kind of if you had satellites orbiting the Earth, you could only get the geostationary satellites that are orbiting, right over the equator of the Earth in synchrony with the motion of the Earth. You wouldn't be able to have the polar orbits and so on. So I'm not quite sure how that works for a black hole, and it may not work out. But if you could have orbits that were not purely sort of on the equator of the black hole, then you could do this thing that I'm mentioning of having this kind of bizarre grid of photons that were interacting by light scattering. An incredibly exotic kind of idea of how to make a computer, and something that would be an incredibly inefficient and slow way to compute things. But that would be a way in which you could basically have something that is a computer or mind-like thing made purely out of photons. At least that's my most immediate version of that. Yeah, Asa comments, a black hole's orbit sounds like the most powerful particle accelerator. Yep, yes, it is. I mean, it's a way that a lot of high energy astrophysical phenomena occur is you have a thing that's very massive, and you'll have things that are pulled into orbit around that thing. And as they get pulled in, they get accelerated. And so, for example, when matter is kind of getting sucked into a black hole, it will orbit very quickly. It will orbit so quickly that, for example, it would emit things like X-rays and so on. Just as when you have something, a charged particle like an electron is moving and being held in an orbit, it will emit, it will emit radio waves, and it will emit visible light if it's going even faster, eventually X-rays and so on. And yes, that happens. And yes, you can use, there are high energy astrophysical phenomena that are believed to be associated with matter getting pulled into, sort of spiraling into black holes and so on. Let's see. Well, let's see. This is a question from Aaron. Does time move faster for hotter objects? That's a mess. Well, the answer is no, but the problem is, okay, in the sort of the basic setup of relativity theory of special relativity from 1905, it's based on the following observation, that the speed of light, however fast you're moving, when you emit light, the light always goes at the speed of light relative to you. So, for example, if you're dealing with sound waves, a sound wave is a wave of compression and rarefaction in the air. A sound wave is sort of a feature, it's something that is kind of locked into the air in the room. So if we've got air in this room, and on average, the air in this room is stationary. The individual molecules, yeah, they're moving around very rapidly, but on average, there are as many molecules moving left as moving right. On average, the air in this room is stationary. So when a sound wave goes through the air, the sound wave is always kind of, it moves at the speed of sound relative to the air. So if I'm moving quickly through the air and I'm speaking, for example, the sound wave I produce is still going to go at the speed of sound relative to the air, relative to being stationary, not at the speed of sound relative to me, the moving me. If I was moving at 100 miles an hour, for example, and going yak, 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 the sound wave I produce will still go at, whatever it is, 550 miles an hour relative to the stationary air in the room, not relative to me. And that's why, for example, when an airplane goes faster than the speed of sound, all those sound waves kind of pile up because it's producing sound waves. It's making a sound as it goes through the air, but those sound waves they're moving only at the speed of sound relative to the stationary air, not at the speed of sound relative to the airplane. Okay, so the big observation that launched relativity is that in the Maxwell's equations for electromagnetism were invented in the 1870s. In those equations, it is the case that however fast you're moving, if you emit light, the light will be going at the speed of light relative to you. And so that idea is like, how can this be? Because if that's the case, how does it manage to be the case that, how does that all work out? Because if you're moving quickly and, how can it, and you're emitting light, how can that light be still going at the speed of light relative to you, even if you were yourself going at half the speed of light? And so what Einstein figured out is that if you change the definition of length and time, everything can work out just fine. And so what happens is time is dilated. I mentioned that. Space is contracted. If those things happen, then you maintain the consistency of the speed of light is constant for an observer in any state of motion. Now, the way this works in our theories of physics, maybe I shouldn't get into this. It all has to do with causal graphs and so on. It's rather lovely how one ends up with that same situation in these kind of systems where one is continuously rewriting the structure of space and so on. Okay, why does this have anything to do with temperature and hot objects? Well, the problem is that the definition of temperature is the temperature is associated with the motion of all those little molecules, for example, in a room. The faster the molecules are going, it's the average energy of those molecules as they run around, that defines temperature. And so in order to have a notion of temperature, you need to have a kind of an extended material, like a gas, for example. And then you could say the gas is this temperature, the gas is that temperature. And it has to have things that bounce around, it has to have walls, and it has to be sort of enclosed in some way. You don't really get to say that individual electron has a temperature. That doesn't really mean anything. You could say that individual electron has a certain energy, and that energy is the average energy for things bouncing around at a certain temperature. But you have to have this whole notion of things bouncing around in a whole collection of different pieces in order to really define a notion of temperature. Okay, so the problem is that if you are using kind of relativity theory and so on, the theory of what happens to extended objects is pretty complicated. Let me give you an example. I actually just found, I've been looking at a bunch of work that I did many, many years ago, and I had an unfinished paper that I wrote in 1983, I think, which was called Realistic Relativistic Matter. And that paper was supposed to be about the question of what is it really like to have matter, like a solid object or a gas for that matter, and have it go at at something close to the speed of light. What is that really like? For example, a solid object, how does it work when it goes close to the speed of light? Let me give you an example of why things get really screwy. So let's imagine you have a solid object. You say, it's all good, I've got a solid object, I've got this big pole, and it's a long pole, and it's a solid. And I start spinning this pole around. And so at the center, I'm just spinning the pole at a certain rate. The center of the pole, the place where I'm spinning it, it's going, pretty fast, but not so fast. As you go further and further out on the pole is going to be going faster and faster and faster until eventually the tip of the pole will be going faster than the speed of light. So how does this work? Because we've got a solid object that's supposed to be a rigid, solid thing. We're turning it slower than the speed of light in the middle, but by the time you're far out, it's going faster than the speed of light. What does it actually do? So what it actually does is the pole falls apart. In other words, the internal stresses on the pole eventually become, if the pole was going to be eventually going, if the tip was going to be going eventually faster than the speed of light or at the speed of light, there would be infinite stresses in the pole. So any material object will fall apart if you try and make it go close to the speed of light. So it becomes very difficult to define what you mean by material objects when you deal with things going close to the speed of light and so on. And so this question, it's actually a long time question. When you have length, for example, or time, these both transform relativistically in the sense that if you go at a certain velocity, so you go at a fraction, well, the usual symbol used is beta, a fraction beta of the speed of light, okay? Then there's just a formula that says that if you go a beta of the speed of light, it's the formula for the rate of time, 1 unit of time is then 1 over the square root of 1 minus beta squared. That's just the formula in relativity theory. If I had kind of a thing I was drawing on, I could probably even explain why the formula works out that way. It's a really quite simple geometrical argument in the end. It has to do with essentially a right-angled triangle, and that's a side length on the right-angled triangle. That's square root of, well, it's what at least the denominator, the square root of 1 minus beta squared is that. So in any case, the actually no, it's one of the side lengths. If the hypotenuse is 1, that's what you get for one of the side lengths. So anyway, the thing that what's the point? Something like length transforms relativistically according to that formula. Same with time. For reasons that I don't think were clear before our recent physics project, energy transforms like time and momentum transforms like length. The fact that those things were in exact correspondence in the way they transform relativistically is something that's easy to understand from our model of physics. I actually looked at what Einstein said about why they transform the same way, and he just says, well, we'll just assume they do this. He doesn't really offer an explanation for why the transformations should be the same. So the next question is, well, how does temperature transform? So let's say you have, and by the way, I should say that one of the features of the transformation of length and time is that essentially, as you go at a speed close to the speed of light, you're kind of trading off length and time. You're going further in length, less far in time, these kinds of things. There's a definite kind of trade-off that happens. Okay, so for temperature, how does temperature transform relativistically? Basically, nobody knows. That's not a very well-defined, it's not a thing that's where there's a good, clean theory of what happens. It's something where if you have this box of gas and you move it at a high speed, well, you've got all these assumptions about, what happens to the sort of the container of the gas? What happens if when you have an extended object and you're looking at that extended object, you see it by light coming from the different parts of that object to you. And so all kinds of weird things happen. Like if you have a cube going close to the speed of light, the cube will appear to be rotated because the further away parts of the cube, their light comes to you, it takes longer to get to you, and so on. So a lot of weird effects associated with an extended material object going at something close to the speed of light. So it's not really clear how temperature transforms. So this question of whether there is a relativistic temperature change, gosh, it's really hard to say because you're moving the whole object, and it's hard to say. I don't really know quite how to unscramble that. Now, when it comes to extended objects moving close to the speed of light, this was something that was studied for a long time, and back in the 1960s and so on. And one of the kind of extended objects were strings. So that what people imagined was you have this one-dimensional thing, this kind of piece of string, and it's moving at the speed of light, and it's kind of wobbling around as a string, but the string sort of has this world sheet, as it's called. If you look at the space-time thing that is sort of carved out by this moving string, it's this kind of sheet in space-time. And so people tried to get kind of a consistent theory of how strings would move at the speed of light as extended objects. And it turns out to be a very complicated story. And that is the origin, that's one of the origins of string theory. And there are many consistency conditions about when these strings really move in a consistent way and have motion that works consistently. And that's what ends up with string theory needing to be in like 26-dimensional space in order to avoid inconsistencies associated with the way that these extended string objects move in physical space. So the whole theory of extended objects in relativity is really a complicated thing. And even the special case of the string moving relativistically, that story is already sort of ends up turning into the story of string theory. So it's a very complicated mathematical structure, and it becomes very difficult, in the case of string theory, one just says, imagine there's a string like this. But in the case of just sort of talking about an extended object, an imaginary spacecraft traveling very close to the speed of light, it's made of, whatever the spacecraft is made of, metal or something like this. It becomes difficult to describe what will happen. And as a practical matter, in many kinds of situations, the metal will always fall apart because metal has only, the metal has only a certain fixed amount of force between the atoms that holds it together. But the result of kind of gravitational, of the forces that are associated with motion close to the speed of light will necessarily be greater than anything that holds the thing together by forces between the atoms. So, complicated answer. Let's see. William observes, doesn't a black hole have a temperature? What happens to the black hole's entropy? Okay. All right. Let's see if I can do this. Okay. Temperature is normally associated with average kinetic energy of particles bouncing around. So you have particles of gas in a box, you heat it up. What's happening is the walls of the box are getting hotter. They have molecules bouncing around faster. Every time a gas molecule hits the wall, it might get a little kick of energy from one of the particles in the wall. And so it goes a bit faster. And then pretty soon the molecules in the gas are going at a higher speed. So that's the ordinary definition of temperature. Okay, so you can also just say, imagine, well, you could, yeah, that's the ordinary definition of temperature. Just sort of particles bouncing around with a certain average kinetic energy. Okay, black holes. Here's a tricky thing about black holes. Usually, black holes just, everything that gets near a black hole gets pulled into the black hole. The gravity of the black hole just pulls it in. And as soon as it goes past the event horizon of the black hole, you on the outside of the black hole never get to see it again. Now, things are a bit tricky, as they usually are in relativity. Something that is going to fall into a black hole, for you as an outside observer, you'll always see it hovering on the edge of the event horizon. To you as an outside observer, you'll never actually see it go into the event horizon. That takes an infinite time to you as an outside observer. But in any case, conceptually, it's as if the thing falls into the event horizon. For the thing itself, it will, in its time, fall through the event horizon, but time is dilated for the observer at a distance relative to the observer who's actually falling into the black hole. Okay, so in any case, in a first approximation, everything falls into a black hole. Okay, or everything that didn't have that, yeah, so, okay, now here's where things get tricky. In quantum field theory, the vacuum, okay, so this is actually a bit clearer in our models of physics than it has been in traditional quantum field theory, but let me explain the traditional quantum field theory case, which is what people usually talk about when they talk about black hole temperatures and black hole entropies and so on. So what happens is, you think you've got a vacuum where there are zero particles, but the way quantum mechanics works, you never get to have a certainty of anything. So in fact, even in the vacuum, there are always these particle-antiparticle pairs that are forming and then annihilating again, forming and annihilating again very quickly. These are so-called virtual particles that just come into existence for a very short time and then are destroyed again. And so in the vacuum, everywhere in space, in the vacuum, in standard quantum field theory, you have an infinite collection of these particle-antiparticle pairs being produced and then annihilating again. In our theory of physics, by the way, that process of the particles coming into existence, being destroyed again, there is energy associated with those particles. And one of the problems in traditional physics has been that that energy produces a gravitational force that will curl the universe up into a tiny ball. So it's been very obscure why that doesn't make the universe basically tiny. Well, in our theory of physics, what's happening is that the structure of space is being sort of knitted together by these rewritings of this network that on a very small scale is what space is made of, so to speak. And those rewriting events both produce space and represent those virtual particle-antiparticle pairs. So in a sense, whereas in traditional physics, space is just put in there, and then we have the virtual particle-antiparticle pairs kind of happening on top of space. In our model, space is made from essentially the same process that is that virtual particle-antiparticle pair process that's going on. So, but in any case, the basic point is, however you look at it, there's these virtual particle-antiparticle pairs that are getting formed all over the vacuum, all over space. So what happens if that happens right at the event horizon of a black hole? What can happen is there are two members of that particle-antiparticle pair, the particle that's an electron and the antiparticle positron, let's say. If you align things up just right, the positron might fall into the black hole, and it was going to annihilate with the electron, but it never gets to do that because that positron got lost inside the black hole. And so the electron is stuck on its own, and that electron just sort of appears as a thing that sort of emerges from the black hole. And so Stephen Hawking back in 1972-ish had this calculation of how that would work. I have to say, I wasn't at all sure that that calculation, no, it was later than that, 76, I think, maybe even. Because I was already doing physics stuff by that time. I certainly wasn't sure that that calculation was actually right. And then it got done in many, many different ways. And nobody's actually observed the Hawking radiation from a black hole, but it's something that it looks pretty solid. There are lots of different ways of calculating it, and they all seem to give the same answer. Now, the thing that's mysterious, well, okay, this is again rather complicated, but the fact that these sort of electrons just sort of come out of a black hole and so on kind of doesn't feel right for quantum mechanics. Quantum mechanics has this idea of, oh, there's an electron, there's a positron, they're very coherent with each other. They're very sort of fundamentally correlated. And that coherence is kind of broken by the presence of the event horizon of the black hole. And so it's always been a bit mysterious how that works, how you get, it's the so-called information paradox of black holes, that you can end up with something where there's sort of a quantum coherent thing, but then the black hole forms, and then that quantum coherence is somehow broken. Well, okay, what happens in our models is, this is going to get too weird. There is not just one event horizon in a black hole. There's an event horizon in physical space, and there's also an event horizon in what we call branchial space, which is essentially the space of quantum branches. And let me not try and explain that in detail right now. It'll take a little while to explain that. But the basic point is that just as I mentioned that in physical space, to an outside observer, the kind of any particle that's going to fall into the black hole appears to be sort of frozen right at the edge of the black hole, right at the edge of the event horizon for an infinite time. Well, one of the things that will happen is that not only will that particle be frozen, but also if you have kind of a quantum measurement, something which is trying to decide whether a particular quantum process happened or didn't happen, a measurement, a quantum measurement, that will also get frozen. And so kind of the image of it is that the observer who is trying to observe what happens with this black hole will be stuck, essentially, not, as one could put it, not sort of being able to form sorry, 1 second. Not being able to sort of form a classical thought, that the observer, just like the sort of particle appears frozen in space, so an observer, their sort of thought processes will be frozen in the same way. And so it turns out you can sort of resolve this paradox of, oh, is it quantum, is it not? How does that work? By thinking in those kinds of terms. But let's see, what was the original question about, oh my, what was I even answering here? I got this, oh, black hole temperature, yes. So okay, so what happens is black holes, because of this process of, vacuum fluctuations, one part of the vacuum fluctuation is pulled in through gravity inside the black hole, the other one escapes. That causes black holes to produce a certain amount of emission of radiation, which turns out to be radiation that is distributed in the same frequency distribution as when light is emitted from a hot object, so-called black body radiation. And what happens is, as the black hole gets smaller and smaller, the intensity of radiation emitted gets higher and higher. And so the expectation is that black holes that will gradually get sort of eaten up. But for a big black hole, the rate of radiation is absolutely tiny. As the black hole gets smaller and smaller, the rate of radiation gets faster and faster, until eventually the black hole will kind of disappear in a blaze of radiation. And for black holes, if there were black holes that were about the mass of Mount Everest that had been created in the early universe, they'd be kind of exploding like that right around now. We haven't seen any of such explosions, but who knows? I think in our models of physics, there are some additional things. There's a thing that I was calling the black hole wind, which is kind of this process where you get essentially gravitational radiation emitted as there's a quantum gravitational effect. that you have essentially gravitational radiation being emitted by a black hole. When black holes merge, what's been observed by the gravitational wave detectors is the very intense emission of gravitational waves when black holes merge. And for example, the first black hole merger, an amount of mass about the mass of the sun was destroyed in a matter of a few seconds and turned into gravitational radiation. So hugely intense amount of gravitational radiation. This black hole wind that I'm talking about is a very light amount of gravitational radiation. Okay, one comment about entropy. I was literally doing something on this afternoon, actually. Okay, so entropy is this idea that has various tentacles, but its basic idea is if you've got a thing, a configuration of gas, you've got all kinds of molecules in a box of gas, the entropy is counting the number of possible configurations of those molecules that are consistent with saying, I've got 1 trillion molecules in a 1 centimeter cube box. The molecules can be going this way, they can be going that way, they can be arranged in different ways. But what you can do is count the number of ways they can be arranged, and you take that number and you take its logarithm, then that gives you the entropy of the gas. So the logarithm is saying, if you say, let's say you had just a collection of particles, and each particle could either be in an up position or a down position. And let's say you have 3 particles, they can each be either up or down, then the number of possible overall configurations is like up, 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 down, down, up, down, up, et cetera, et cetera, et cetera. There are 8 possible configurations. And in general, if you have n things that can be either up or down, there are 2 to the power n, 2 times 2 times 2, n times possible configurations of that whole object. And so the logarithm, for example, log to the base 2 of 2 to the n is just n. The logarithm is just telling you the exponent. It's telling you the number of times you multiply things. So when you have particles in a box, essentially every particle you add, it gets to decide what it does. And it's kind of multiplying the number of possible configurations of all the existing particles. So by taking that logarithm, you're roughly counting the number of particles, the number of degrees of freedom that the system has. And so entropy is always this count of the number of degrees of freedom that a system has that are consistent with some constraint that you've given on the system. Like you say, it's a box that's 1 centimeter across. It's a box that's 2 centimeters across. It's this material that is made from these, where the molecules are arranged this way. It's a material where the molecules are arranged that way. The entropy is the number of degrees of freedom, the number of different, of independent things you can change consistent with the constraints that you give. Okay, so does space-time have an entropy? Well, in our model of physics, it does, because in our model of physics, space is made from this giant network of points, of elements. And so if you say, well, I've got a box of space, I've got a region of space, and it's this size, we can just count the number of possible kind of webbings, the number of possible networks that are consistent with a box of space of that size. Now, it's a little tricky because the actual structure of space determines one's notion of size. There's a bit of fancy footwork there, which actually I don't completely know how to do yet. But roughly, you can simply count the number of configurations of the network, and that gives you, effectively, you can use that to compute the entropy of a box of space. Okay, now usually it's a little bit hard to know what you mean by a box of space. The one case where that's not hard to figure out is a black hole, because a black hole is a well-defined event horizon that says this is a region of space that's inside, there's a region that's outside, and so on. So a bit of a cliffhanger here, because I don't actually know how to compute the entropy in our models for a black hole. Hopefully somebody will figure out how to do that. And my guess is, I'm fairly certain, that the answer will be the same as the answer that one gets from the calculation that deduces entropy from temperature from this black hole, Hawking radiation, and so on. But so the idea of the entropy of a black hole is to say, what are the number of configurations of the structure of space consistent with the fact that there's a black hole there? And there may be many different configurations of space that all lead to that same structure of the event horizon. Just like there are many different configurations of the gas that all say, oh, there's just gas molecules enclosed in this box. Now, that's a very new kind of our model of physics explanation of black hole entropy, I think it's right, and I think it's much clearer than what's been known before. What's been known before is kind of a very indirect, circuitous path where you deduce the entropy from knowing things about the radiation. But I think you can say it quite directly, and that's what it's due to, is that the black hole, I mentioned before, that sort of all black holes look the same. They're defined just by their mass and their spin rate, their angular momentum. But that's not strictly the case. When you get up to quantum gravity, then it will not be the case, I think, that all black holes will be the same. Instead, there'll be many possible things that have that same mass and spin rate, and that count of the number of such things will give the entropy of the black hole. Oh boy, there's some. Mean asks, why doesn't the black hole further collapse in on itself? Because this picture of kind of a mechanical collapse isn't really the correct story. The correct story is that, well, the main story is, okay, in the simplest kind of black hole, at the center of the black hole, in traditional theories of gravity, there is a space-time singularity at which the curvature of space is infinite. And what does that mean? Well, when you have an object, it's in space. If it's in flat space, the object just sits there. If the space gets curved, the object is essentially deformed by the curvature of space. And so when you have an event, not an event horizon, this is inside the event horizon, there's a singularity in space-time. At that singularity, space-time is infinitely deformed. So any object that you have is itself infinitely deformed. So that's the traditional view in general relativity. In our models of space, that singularity, which is usually has to be something that is described not with the standard equations of general relativity, of the theory of gravity, because those equations can't describe a singular place. They can only describe continuous changes in the structure of space. In our models, you can describe things which change discontinuously like that, because the whole model is based on a discrete structure of space. In our models, in that kind of black hole, what happens is that this network that represents space gets to a place where it just freezes. There are no more updates that can happen on this network. So what that means is that time stops, because time is the progressive updating of the network. The network represents everything in the universe. The progress of time in the universe is the process of updating that network. So at the center of the simplest kind of black hole, what happens is the network can no longer be updated there, and so time just stops. So if you were approaching that singularity, what would happen is you would just freeze forever. Time would stop. And so that's kind of what happens in the black hole, is eventually just time stops. So there's nothing more that can happen. You're done because time has stopped. And that's a rough explanation. I mean, the story of why the event horizon is of a certain size and so on is a slightly more complicated story. Let's see, is there a simple way to explain that? Not that I can immediately come up with. But that's some version of why the black hole can't further collapse. Usam asks, do the updates to maintain the structure of space explain vacuum energy? Yes, they do. So vacuum energy is this phenomenon that in the vacuum, because of these particle-antiparticle pairs, there's an infinite energy associated with the vacuum. And maybe it isn't completely infinite, but it's very high at least. And our model, where the actual processes going on in the vacuum are what create the structure of space, explain that phenomenon of vacuum energy. Because really what you're doing is you're just looking at things relative to the space that we think of as being there. So the fact that the space that we think of as being there has all this stuff that we might think of as energy associated with it is irrelevant to us, because all we are sensitive to is changes relative to the structure of space as we know it. So that sort of that explains and gets rid of this kind of long time problem in physics of the fact that there's this huge vacuum energy that exists everywhere in the universe. All right, maybe one more question and then I should wrap up here. Well, Prometheus asks, how much more complex are the dynamics of the human brain than the dynamics of a galaxy? You know, it's a funny thing. I think we know now that there are about 86 billion neurons, I think, in a typical human brain. So give or take 100 billion neurons in a typical human brain. Turns out there are also 100 billion stars in a typical galaxy. There are also 100 billion galaxies in the universe. So there's a lot of that number, 100 billion, shows up in a bunch of places. So if you're going to remember kind of a number about sort of science or something, that 100 billion number of stars in a galaxy, number of galaxies in the universe, number of neurons in a brain, they're all about the same. And you know, to assess sort of the question of what's more complicated than what sort of depends on asking, well, what is it that you care about what's happening? If you care only about the motions of stars and you don't care about all those aliens that are hanging out on all those planets around all those stars doing all this cool stuff, you only care about the motion of stars, then you've just got 100 billion stars in the galaxy. But if you care about all those aliens doing cool stuff, then there's a lot more detail and there's a lot more going on there. Similarly, in brains, if all you care about is, well, we don't know exactly what you should care about in brains. There's a lot of fine detail of individual molecules, you know, proteins getting produced in the synapses in brains and so on. We don't know how much of that stuff matters and how much it's just, did the neuron fire or did it not fire? And that's kind of the sort of you know, what level of detail are you looking at is important to understand in assessing that difficulty. Okay, Madoff asks, does a black hole inherit the dimensionality of the space-time it's forming in? Well, okay. In traditional theories of gravity, in the Einstein equations, which are the usual equations used to describe the structure of space and time, those Einstein equations, you have to pick the dimension of space-time before you start. So there's 3 + 1 dimensional space-time, 3 space, 1 time. That's ordinary space for us. In things like string theory, one might look at, you know, 10-dimensional space-time and so on. There are Einstein equations that you can write down for any number of dimensions of space-time. And usually time is just one dimension effectively, and space is all the other dimensions. But but so you get to pick an integer, a whole number, and that's the number of dimensions of space. In our models of physics, that's not the way it works. Because space is formed from this kind of large-scale limit of this underlying network, you can end up with a dimension of space that isn't necessarily 3, it could be 3.1. It could be something where, see, okay, how do you estimate the dimension of space from just, if all you know is points in space, how do you figure out what the dimension of space is? So you just got this big bag of points in space, and all you know is what point is connected to what other point is related to what other point. So a way you can figure out the dimension of space is by just saying, start at a point, go to all its neighbors, then go to all its neighbors' neighbors, then keep going, and ask how many points do you get to by progressively going to the neighbors of the neighbors, the neighbors of the neighbors of the neighbors. Okay, let's say all the points were arranged on a square grid. Okay, so we start at one point, and then we go to its neighbors. There might be 4 neighbors, northeast, southwest. We go to their 4 neighbors. If you're imagining it, you're making this kind of diamond shape. The number of neighbors that you go to goes up like the area of a square. So it goes up like r squared if r is the distance you've gone. Imagine a line. How many neighbors do you get to? Well, you always have a linear number. It just goes up like r. You've just gone a distance r. You've just extended your 3 steps to the left, 3 steps to the right. The total number of things you reach is proportional to r. So in general, as you, on a grid, for example, like let's say a 3-dimensional grid, do the same calculation, you'll find it's r cubed. Okay, but if you just imagine that all you have is points, elements, nodes, and connections, you can do the same calculation, but the calculation has no reason to end up having an answer where the growth rate is an integer, where the exponent, the r to the power d, where the d is an integer. So in our models of space, you can have variable dimension space, and you can have space whose dimension changes over time. Like we think the early universe had infinite dimensional space, which gradually kind of cooled down to be three-dimensional in the universe that we experience today. So in our models of physics, it's possible to have dimension change. The standard theories of space-time simply don't know how to deal with anything other than interdimensional space. There is no theory, nobody knows what the Einstein equations are like in 3.1 dimensional space. The only way we know anything about that is from our models of physics. And we're starting, in fact, one of our projects in the next few months at our Wolfram Institute is to try and do the kind of generalization of calculus that's needed to be able to work out how one thinks about sort of the generalization of kinds of structures of space outside of integer dimensions. So the answer is, for a black hole in ordinary Einstein gravity, or the ordinary equations of gravity, you first have to pick the dimension of space, and then you make up your equations. And in different numbers of dimensions, there are different kinds of black hole structures. So for example, in 3 dimensions of space, 1 dimension of time, you have the ordinary black hole, you have a non-spinning black hole, you have a spinning black hole. When you go to different dimensions, I think in 4 dimensions of space or 5 dimensions of space, you get these things that are called black Saturns, which are things that have sort of a central black hole that are like the black holes we have in three-dimensional space, but they also have this kind of Saturn's rings like other black thing that's sort of a torus around the main black hole. That doesn't happen. The structure of the event horizon isn't like that. In the case of, well, a spinning black hole, even in 3 dimensions of space, has a more complicated structure. It's the so-called Kerr solution to the Einstein equations. And it has an inner event horizon, an outer event horizon, and it has a lot of exotic stuff that goes on. And you can have exotic things where there's a crossover between an inner black hole and an inner white hole, all kinds of exotic things. It's all happening inside an event horizon. You don't get to report on it. Well, more or less. People thought that the singularity that could exist at the center of a black hole could never be naked. It could never be without an event horizon. Turns out there's an elaborate construction that you can make that allows you to form a naked singularity in ordinary Einstein gravity. That formation of a naked singularity is a very elaborate, delicate process. You have to be adding a little piece of matter here, a little piece there, a little piece there. You got to make sure nothing bad happens. You add these things in exactly the right way, and you'll get a naked singularity. It's kind of a little bit like if you want to reduce the temperature of an object to absolute zero, where all the molecules are essentially stationary, because you've taken all the heat out of the system. That's something that takes a lot of effort. You have to say, that molecule, oh yeah, let's zap that one. Oh yeah, let's zap that one. It becomes increasingly difficult to do that as you want to get to absolute zero. And it's the same thing if you want to form a naked singularity. I don't know what the actual structure of naked singularities is outside of 3+1 dimensional space-time. I would imagine the same constructions work. They might get easier in higher dimensions. I'm not sure. It might get harder as well, because I can imagine arguments for both things. I don't know the answer to what happens, and I'm not sure if it's known. But in any case, outside of 3 dimensions, there are different kinds of singularity structures that can exist, different kinds of event horizons that can exist. What those look like in like 3.1 dimensional space, we don't yet know. We'd like to know. In fact, that will be if it turns out. Actually, I hadn't thought of this before. Yeah, if it turns out, so one of the things that's of great interest in our models is to try and detect dimension fluctuations in the universe. And we think there might be a way of doing that by detecting what a dimension fluctuation does to a photon from the cosmic microwave background. But it occurs to me that if something funky happens with the event horizons of black holes, it could be the case that a black hole formed very early in the universe would be formed in a region of space-time that was still sort of a fluctuating region of space-time that had dimension 3.01, for example, and wasn't really close to 3 dimensions. And it could be the case that there is some exotic effect that comes from the formation of a black hole in 3.01 dimensional space-time, which right now we have no idea how that works. I mean, in our models, we can simulate it numerically with a small number of elementary elements in space. The real number of elementary elements in space is absolutely huge, but we can do a computer simulation for a small number and we can kind of see what happens. And that's an interesting idea that perhaps if there is some kind of anomalous behavior of a black hole in just away from three-dimensional space, and that could have an effect of gravitational lensing, for example, effect that could be visible in gravitational lensing from very early in the history of the universe. So that's an interesting idea. Thank you all implicitly for providing that that idea, because we're really interested in, what's the microscope that allows one to see down to that microscopic structure of space. Just like when we're looking at a fluid like water, how do you know it's made of molecules? Well, there are these exotic experiments like Brownian motion, where you have you see a pollen grain being kicked around. We need to find the analogous exotic experiments that give us this way of seeing what happens in physical space and seeing down to the kind of molecular structure of physical space. Okay, there's a comment here about William says the number of atoms in a bacterium is also about 100 billion. That's interesting. I didn't know that. Let me see. Can I estimate that? A bacterium is like a micron across, I think. And that would be, so that is one micrometer, if I'm right about that. And that would be 10 to the minus 18 cubic meters. And then the number of, in that volume, if it's density 1, which it probably isn't, but let's say it is, that would be 10 to the minus 18 grams. And that would be, so the number of molecules in a gram is 6 times 10 to the 26. So let's see, that's about, yeah, we're getting roughly that number. I'm not quite sure if it's landing quite in the right place. Oh boy, William is, you see, this is something I'm pretty sure if you type into Wolfram Alpha 100 billion meters, 100 billion atoms and things, it better give comparisons that start listing these off. I better try that. That's a good, that's a good suggestion here. All right, one last thing here. Let's see. The doctor says, as gravity increases and or speed increases, time is constant to the participant, but on the outside, space and distance could be greater or lesser. If you had a light year cube of space and shrunk it into a meter, light would take the same time to go through it. Well, how do you shrink that light year of space? I mean, that's the issue. I mean, I think this question about sort of expanding and contracting space, that's a very weird concept because we're in space, right? And so let me just mention one thing. People say the universe expands. Say, so what on earth does that mean? If everything in the universe expands, how do we know that anything is expanding? Because we'd be expanding too. In fact, in our models of physics, it is possible that the universe is expanding everywhere at an incredibly rapid rate, and that at every moment in time, we are made from more and more and more atoms of space. We're expanding rapidly. But we don't know this because everything in the universe is expanding the same way. So we only get to sense things where there's a difference in the expansion rate between one thing and another. And so the expansion of the universe that we already know about, the thing that happened that started in the Big Bang, that expansion is an expansion of things that are not otherwise being held together. So for example, galaxies do not expand. Galaxies are held together by the force of gravity and they don't expand. But a cluster of galaxies doesn't expand much. If you look at between clusters of galaxies, the distances between clusters of galaxies do increase. And what really happens is that the expansion of the universe is like another kind of force of gravity that's pulling things apart. And there's a small force that does that. And that force is being balanced against forces that hold things together. So the force that holds us together, the interatomic forces that hold a sort of standard solid material object together, are unbelievably much stronger than the forces that are the forces of expansion of the universe. And we only get to see the expansion of the universe when we're at a scale where even gravity doesn't affect that. So this question about saying, well, can you take a block of space and change its size? That's a very slippery question. And really the only way that we get to make boxes of space that we know of is in black holes, because the event horizon defines this kind of the boundary of the box. Now, it's an interesting question. I will say, back in 1981, I wrote a couple of papers with a friend of mine named Jan Ambjorn, who about, it was called Properties of the Vacuum. And so we had part one was called Mechanical Properties of the Vacuum. We were interested in vacuum fluctuations and associated with, you put the vacuum in a metal box and you just sort of change the size of the metal box. What happens? How does it affect the volume of vacuum that's inside the metal box? And we figured out some kind of interesting things. Then we started, the part two was the electrodynamic properties of that. If you put an electric field, you constrain it with an electric field. What happens then? All kinds of other exotic phenomena. We had promised a part three in that series of papers back in 1981 that was going to be about the gravitational effects of these things. Well, we never wrote it. And it turns out, with our model of physics, I think we're finally in a position to write that paper. And so I might, if I have the time, I've been telling my former collaborator, Jan, that we should do this for a number of years. And he doesn't believe me when I say, look, I'm pretty efficient now at doing science and things like that. You know, maybe I will take a vacation weekend, so to speak, and try and churn this out. He doesn't believe that, but we'll see. It's kind of a vacation on studying the gravitational properties of the vacuum. But I think now we're finally in a position to do that. And this notion of what does a box of vacuum look like? You know, you can constrain a box of vacuum with event horizons. Can you constrain it any other way? Can you describe the size of a region of space by some method other than that? And maybe you can. Maybe you can have something where you have essentially test particles and you're describing the size of this region of space by asking where the test particles go, which is essentially a statement of the structure of the curvature of space-time and the gravity in space-time. I'm not sure. I mean, that's a good question. Can one sort of discuss the kind of the size of boxes of space? You know, space, even in the standard theory of gravity, is a little bit like an elastic medium. It's a little bit like some kind of deformable material, although it has rather different, strange characteristics with respect to that. And it's, as I was mentioning, realistic relativistic matter, which is an interesting point, that we don't know how to explain what a solid, like a thing held together by interatomic forces, what that is like relativistically. The one kind of material that we know how it works relativistically is space-time. And it has its own constitutive relations, as they're called, that relate kind of stresses and strains and things like this. And it has those things, although it's pretty exotic relative to material objects. And one of the big questions, actually, in studying, even in traditional theories of gravity, is just what kinds of material can exist in space-time. So two of the characteristics are the pressure and the energy density. So one of the things that's always assumed is that the pressure of anything is less than 1/3 of its energy density, where energy density is measured in units with speed of light squared and all kinds of other equals mc squared like stuff. But for a radiation gas like photon gas, P, the pressure is equal to 1/3 of the energy density. And it is believed that you can't have any kind of material stuff where the pressure is larger than the 1/3 of the energy density. So in other words, there's no way to make that out of any kind of stuff in the universe. So it's an interesting question, which I don't know the answer to, whether in our models of physics, it's possible to get P greater than 1/3 rho, pressure greater than 1/3 of energy density. It's an interesting question. That should be looked at. All right, I should wrap up here. Thanks for all those comments. Oh, I see somebody pasted the result from Wolfram Alpha for 100 billion. I think we should add a couple of comparisons there. I think more are known. And one was suggested here about atoms in a bacterium. All right, well, thanks a lot to everybody, and see you another time, and bye for now.